All right, hi everyone. So I slightly changed the topic in agreement with the organizer, so thank you. Today my talk will be about the possibility that Super-Eddington accretion may explain the X-ray weakness of the little red dots. So we already all heard several talks about the little red dots. I will just stress that JWST type 1 AGN are generally undetected in the X-rays, even in stacking analysis, leading to the so-called X-ray weakness problem. So for the first time, we investigated this phenomenon using GRR MHD simulations of Super-Eddington accretion onto 10 to the 7 solar mass black holes at redshift 6, representative of the median population. And the punchline is that we obtain SCDs that are extremely intrinsically X-ray weak, especially accreting at mildly Super-Eddington accretion rates, so just above Eddington, with zero spin and viewed at large inclination angles from the jet. So we obtain X-ray bolometric corrections 2 to 10 kb. This is in dress frames that are very large. In particular, this plot shows the bolometric corrections as a function of the log of the Eddington ratio for different spin values and for different inclination angles. Now, without going into too many details, you can see that very large bolometric corrections can be obtained in excess of 100 for accretion rates just above Eddington. And if we shift these SCDs at redshift 6, for example, because they are very steep and soft, they get completely shifted out of Chandra's band. And you can easily obtain bolometric corrections that are even in excess of 10 to the 4. So how do the SCDs look like exactly? So this plot shows our reference SCDs for X-ray weak on the left and X-ray strong on the right, simulations at redshift 0. And in particular, the red line shows the average over the solid angle. The different gray lines show the SCDs as viewed from inclination angles between 10 degrees and 80 degrees. As you can see, X-ray strong SCDs are extremely, very powerful in the X-rays, have even a high energy bump if seen close to the pole. And these features are completely absent in the X-ray weak SCDs. And if we shift, again, these SCDs at high redshift, you can see that the X-ray weak SCDs are basically almost completely invisible by Chandra, except if seen very close to the pole, but they can be completely observed at an inclination angle by future X-ray observatories. So exactly how steep are our SCDs? This plot shows the photon index, gamma, for all our SCDs, and you can see that most of them have gamma values in excess of 2. Typical values for AGN are 1.7, 1.8, and actually the most common value is 4.4, extremely X-ray weak, extremely steep. The beaming effect, so the fact that the SCD changes as a function of the inclination angle, is also very important. And in particular, the same supermassive black hole with the same accretion rate leads to a factor of about 30 in difference in the peak luminosity if the inclination angle changes between 10 and 80 degrees. So the inner structure of the accretion flow shows the physical reasons behind the differences in X-ray weak and X-ray strong cases. And in particular, you can see the X-ray strong cases show much hotter temperatures and also a much more relativistic jet. So to conclude, what is the direct application to the little red dots, or in general to AGN, type 1 AGN by JWST? This plot shows the bolometric correction observed 2 to 10 kb for samples from Maiolino and Yue. You can see also the X-ray stack here, and this is the weakest X-ray detected AGN type 1. And in particular, you can see that our SCDs with their bolometric correction observed are shown here in blue dots. So as you can see, our SCDs can explain not only the single sources, but also their X-ray stack. So thank you.